We end the lesson by revisiting the strain energy one more time, but this time for a non-linear materials. And this is really, really cool, I think. We're going to come back and look at this cable problem as a linear expression when we go back to chapter 3. But let's jump into the nonlinear stuff so that it really links up nicely with your 502 course. So we start with the same premise here. It's the summation of all these individual integrals, pi d delta I. But stress is force over area for an axial member here. This is axial loading, of course, not bending. So P is sigma times A. So I could replace the P with a sigma A in here. And the fantastic thing that I want you to appreciate is that sigma can be a nonlinear. Okay, so sigma is a function of epsilon. We remember that from Hooke's law in week 1 and 2 of this course. But we need deltas, not epsilon in here. So maybe hit the pause button and think, well, how am I going to get delta from epsilon? This is one of the classic questions that I've asked so many times, and it's such a simple answer, but often people just get stumped by it, okay? So the question is, I have an epsilon in here, how do I get deltas? So when you're ready to unpause it, go ahead and hit play again. The answer, of course, is that epsilon is delta over L. You knew that, right? So in this example, we have sigma is some function of epsilon. It's a nonlinear function here. You could see that. So our force is a nonlinear function of A, but still it's a function of epsilon. So I swap out delta over L for the epsilons. And there's one little tricky part in here. We really have to make sure that we are careful with our limits of integration here. And I was a little loosey-goosey with it, so I'm going to really try to use capital deltas on these. So I have the two functions of the two parts of the integral, excuse me, here. And if we had two cables, oh, that was in this example, there's two cables, sorry. And then there's the two integrals for that. So you could express this and evaluate this. It's really nice, I think. Just a quick warning, though, that little geometric trick of arc lengths becoming straight lines might begin to decay if this nonlinear expression is too nonlinear, okay? We're always having still small deflections. That's a key point for the geometric analysis. All right, good luck with that.